Welcome to the Layer 2 Networking module of the Networking Fundamentals for Industrial Control Systems course. The goal of this course is to enable learners to assimilate the information presented in further training courses such as the Managing Industrial Networks with Cisco Networking Technologies. This module presents a deeper view of Layer 2 networking and the Ethernet protocol. As a network operator, understanding these concepts to facilitate day-to-day operation and troubleshooting tasks is important. After you complete this module, you will be able to describe Layer 2 networking and the Ethernet protocol, identify basic switching functions and VLAN concepts, and describe common redundant LAN topologies and Ethernet resiliency protocols. In this lesson, you will be introduced to local area networks, or LANs, the typical components of a LAN, and the Ethernet protocol. You will also learn about media access control addressing and forwarding functions including unicast, multicast, and broadcast. LANs can vary widely in size. A LAN may consist of only 2 computers in a home office or small business, or a LAN may include hundreds of computers in a large corporate office or multiple buildings. The defining characteristics of LANs, in contrast to WANs, include typically higher data transfer rates, smaller geographic area, and a lack of need for leased telecommunication lines. A small home business or small office environment can use a small LAN to connect 2 or more computers and to connect the computers to 1 or more shared peripheral devices such as printers. A large corporate office can use multiple LANs to accommodate hundreds of computers and shared peripheral devices spanning many floors in an office complex. Every LAN has specific components, including hardware, interconnections, and software. Regardless of the LAN size, a LAN requires these fundamental components for operation. Those include endpoints, interconnections, network devices, and protocols. Endpoints are devices that are connected to the network that send and receive data, such as computers, tablets, IP phones, smartphones, sensors, and machines. Interconnections allow data to travel from one point to another in the network. Interconnections include these components: network interface cards and network media. Network interface cards, or NICs, translate the data that is produced by the computer into a format that can be transmitted over the LAN. Network media, such as cables or wireless media, transmit signals from one device on the LAN to another. A LAN may also include these network devices: Ethernet switches and network routers. Ethernet switches form the aggregation point for LANs. Ethernet switches provide intelligent distribution of frames within the LAN. Routers, sometimes called gateways, provide a means to connect LAN segments. Protocols are sets of rules that govern data transmission over a LAN and including Ethernet protocols, IP, ARP, and DHCP. We will discuss these rules and other concepts as we continue, but we will begin by exploring the Ethernet protocol. Ethernet is one of the most commonly used protocol standards in the local area network. The mechanical properties of Ethernet depend on the type of physical medium in use, with coaxial, copper, fiber, and wireless media available. Although wireless is increasing in popularity for desktop connectivity, copper and fiber are the most popular physical layer media for network deployments. Ethernet was originally based on the idea of computers communicating over a shared coaxial cable acting as a broadcast transmission medium. Originally, the shared coaxial cable of an Ethernet, or the shared medium, connected every attached machine in a building or campus. A scheme known as Carrier Sense Multiple Access with Collision Detection, or CSMACD, governed the way in which the computers shared the channel. The Ethernet physical layer evolved over a considerable time and now encompasses many physical media interfaces and several magnitudes of speed. Fiber optic variants of Ethernet offer high performance, electrical isolation, and long distance, tens of kilometers with some versions. In general, network protocol stack software works similarly on all varieties. Through the first half of the 1980s, the 10-base-5 implementation of Ethernet used a coaxial cable with a diameter of 9.5 mm, later called thick Ethernet or ThickNet. In the media specification 10-base-5, the number 10 refers to the speed of the connection at 10 megabits per second. The term base refers to the media being used as a single shared digital connection, and the number 5 refers to the distance of the cable segment between repeaters, or in this case, 5 times 100 meters. The successor, 10-base-2, also called Thin Ethernet or ThinNet, used a cable similar to the television cable of the era. The emphasis was on making installation of the cable easier and less costly. Modifying Ethernet to conform to the twisted pair telephone wiring already installed in commercial buildings provided another opportunity to lower costs, expand the installed base, and leverage building design. Twisted pair cabling is a type of wiring in which two conductors, the forward and return conductors of a single circuit, are twisted together for the purposes of canceling electromagnetic interference from external sources. Thus, twisted pair Ethernet was the next logical development in the mid-1980s, beginning with Star LAN. Unshielded twisted pair-based Ethernet became widely deployed with the introduction of the 10-base-T standard in 1990. This system replaced coaxial cable systems with a system of full duplex switches linked with UTP. In this specification, the speed is still 10 megabits per second, and the channel is still a shared digital channel. However, the cable distance is only 100 meters and connects through a hub. With the arrival of this standard, Ethernet switches supplemented the half-duplex carrier-sense multiple access with collision detection scheme with a full duplex system that offered higher performance at a lower cost than routers. Ethernet switches capable of mixed speed and mixed duplex operation were built with the release of the 100-base-T standard. The technology has evolved rapidly and supports varying cable length with speeds up to 10 gigabits per second. Copper cabling, if used, is often in the form of specially shielded twisted pair to improve resistance to interference from electromagnetic interference sources such as heavy machinery. Fiber optic systems provided an alternative to using twisted pair cable. An optical fiber is a flexible transparent fiber that is made of very pure glass and is not much larger than a human hair. An optical fiber acts as a waveguide or light pipe to transmit light between the two ends of the fiber. Optical fibers are widely used in fiber optic communication, which permits transmission over longer distances and at higher bandwidths or data rates than other forms of communication. Fibers are used instead of metal wires because signals travel along them with less loss and with immunity to electromagnetic interference. As you can see, Ethernet is an evolving standard with speeds of 40 gigabits per second and 100 gigabits per second now available on fiber connections. Bits that are transmitted over the media in an Ethernet LAN are organized into a structured set of bytes called a frame. In Ethernet terminology, a frame is the container into which data is placed for transmission. The frame contains header information, trailer information, and the actual data that is being transmitted. Here we see the structure and the most important MAC layer fields of an Ethernet frame. Preamble. This field consists of 8 bytes of alternating ones and zeros that are used to synchronize the signals of the communicating computers. Destination address. This field contains the address of the network interface card on the local network to which the packet is being sent. Source address. This field contains the address of the network interface card of the sending computer. Type or length. In the Ethernet 2 standard, this field contains a code that identifies the network layer protocol. In the 802.3 standard, this field specifies the length of the data field. Therefore, the protocol information is contained in 802.2 fields, which are at the logical link control layer that is contained in the 802.2 header and data field. Data and pad. This field contains the data that is received from the network layer on the transmitting computer. This data is then sent to the same protocol on the destination computer. If the data is shorter than the minimum length of 46 bytes, a string of extraneous bits is used to pad the field. Frame check sequence. This field includes a checking mechanism to ensure that the packet of data has been transmitted without corruption. Communication in a LAN network occurs in 3 ways: unicast, broadcast, and multicast. Ethernet frames are addressed accordingly. Here we see the relationship of Ethernet frames to methods of network communications. Unicast is the communication in which a frame is sent from one host and addressed to one specific destination. In a unicast transmission, there is just one sender and one receiver. Unicast transmission is the predominant form of transmission on LANs and within the Internet. For a unicast transmission in a switched network environment, if the switch knows where all endpoints are, the switch only forwards the traffic to the specific host to which the switch is addressed. Broadcast is the communication in which a frame is sent from one address to all other addresses. In this case, there is just one sender, but the information is sent to all the connected receivers. Broadcast transmission is essential for sending the same message to all devices on the LAN. For a broadcast transmission in a switched environment, the broadcast data gets sent to each host attached to the switch. Multicast is the communication in which information is sent to a specific group of devices or clients. Unlike broadcast transmission, in multicast transmission, clients must be members of a multicast group to receive the information. In a switched network, multicast traffic may be treated like broadcast data since the switch is unaware of which endpoints are participating in the multicast. However, in switches that can listen to the multicast traffic with a feature called IGMP snooping, the switches can differentiate which endpoints need to receive the data. The address that is on the network interface card is the MAC address, which is often referred to as the burned-in address since the manufacturer programs the address in. Some vendors allow modifications of this address to meet local needs. There are two components of a 48-bit Ethernet MAC address. Organizational Unique Identifier. This component identifies the manufacturer of the NIC. The IEEE regulates the assignment of OUI numbers. The vendor assigned portion is a serial number that uniquely identifies the Ethernet hardware. The physical address is a binary number that can be expressed in hexadecimal format and is actually burned into the NIC. This address is referred to as the burned-in address or MAC address. As mentioned, this address is expressed as groups of hexadecimal digits that are expressed as quads, with a dot separating each group of 4 hexadecimal digits, or pairs, with a colon or dash separating each group of 2 hexadecimal digits. Note that various systems use various display formats. Each device on a LAN must have a unique MAC address to participate in the network. The MAC address identifies the location of a specific endpoint on a LAN. Unlike other addresses that are used in networks, the MAC address should not be changed unless there is some specific need to do so. In this lesson, you will be introduced to the functions and characteristics of Layer 2 switches, the logical segmentation of Ethernet networks using VLANs, and the function of several switch protocols such as VLAN Trunking Protocol, Dynamic Trunking Protocol, and Cisco Discovery Protocol. When you connect 3 or more devices together, you do so by connecting each one to a shared cable, or you need a dedicated network device to enable communication between hosts. If using a dedicated device, the Ethernet segment may connect to a wiring hub, which has the same effect as having the end host devices connecting to a shared cable. Historically, when network devices connected to a shared cable segment or to a wiring hub, end host devices had to compete for the same bandwidth, and only one device was able to transmit data at a time. Network segments that share the same bandwidth are known as collision domains because when 2 or more devices within that segment try to communicate at the same time, collisions may occur. Using switches as network devices is common today, as well as operating at the link layer of the TCP/IP protocol suite to divide a network into segments and reduce the number of devices that compete for bandwidth. Each new segment then results in a new collision domain. More bandwidth is available to the devices on a segment, and collisions in one collision domain do not interfere with the workings of the other segments. As shown here, each switch port connects to a single PC or server. Each switch port represents a unique collision domain. The broadcast domain is another key concept. The filtering of frames by switches based on their MAC addresses does not extend to filtering broadcast frames. By their nature, broadcast frames must be forwarded. Therefore, a port on a switch forms a single broadcast domain. The port takes a Layer 3 entity, such as a router, to terminate a Layer 2 broadcast domain. Half-duplex communication relies on a unidirectional data flow, where sending and receiving data are not performed at the same time. This behavior is similar to walkie-talkies or two-way radios in that only one person can talk at a time. If someone talks while another person is speaking, a collision occurs. As a result, half-duplex communication implements Ethernet carrier-sense multiple access with collision detection to help reduce the potential for collisions and to detect when collisions are happening. Half-duplex communication has performance issues that stem from the constant waiting because data can flow in only one direction at a time. Half-duplex connections are typically seen in older hardware such as hubs. Nodes that are attached to hubs that share the connection to a switch port must operate in half-duplex mode because the end computers must be able to detect collisions. Nodes can operate in a half-duplex mode if the network interface card cannot be configured for full duplex operations. In this case, the port on the switch operates in half-duplex mode as well. Because of these limitations, full duplex communication has replaced half-duplex in more current hardware. In full duplex communication, the data flow is bidirectional, so data can be sent and received at the same time. The bidirectional support enhances performance by reducing the wait time between transmissions. Most Ethernet, Fast Ethernet, and Gigabit Ethernet network interface cards offer full duplex capability. Frames that are sent by the two connected end nodes cannot collide because the end nodes use two separate circuits in the network cable. Each full duplex connection uses only one port. Full duplex connections require a switch that supports full duplex or a direct connection between two devices that each supports full duplex. Nodes that are directly attached to a dedicated switch port with network interfaces that support full duplex should be connected to switch ports that are configured to operate in full duplex mode. Full duplex communication increases effective bandwidth by allowing both ends of the connection to transmit simultaneously. However, if the duplex settings on the end node do not match those on the switch port, a failure to synchronize exchanges will occur, resulting in loss of data. Switches have become a fundamental part of most networks. The switches allow the segmentation of a LAN into separate collision domains. Each port of the switch represents a separate collision domain and provides the full media to the node or nodes that are connected on that port. The introduction of full duplex communications, a connection that can carry transmitted and received signals at the same time, has enabled 1 gigabits per second Ethernet and beyond. Switches connect LAN segments, use a table of MAC addresses to determine the segment to which the data is to be sent, and reduce network traffic. The following are some important characteristics of switches. High port densities. These switches have 24 and 48 port switches that operate at speeds of 100 megabits per second, 1 gigabits per second, and 10 gigabits per second. Large enterprise switches may support hundreds of ports. The ability to store more received frames before needing to start dropping them is useful, particularly when there may be congested ports to servers or other parts of the network. The switch may possibly support a mixture of speeds depending on the cost of a switch. Ports of 100 megabits per second are expected, but switches offering ports supporting 1 gigabits per second or 10 gigabits per second are becoming more common. Having fast internal switching allows many speeds: 100 megabits per second, 1 gigabits per second, and 10 gigabits per second. Switches provide high port density at a lower cost. For this reason, LAN switches can accommodate network designs featuring fewer users per segment, therefore increasing the average available bandwidth per user. Ethernet switches selectively forward individual frames from a receiving port to the port where the destination node is connected. This selective forwarding process can be thought of as establishing a momentary point-to-point connection between the transmitting and receiving nodes. The connection is made only long enough to forward a single frame. During this instance, the two nodes have a full bandwidth connection between them and represent a logical point-to-point connection. The switch builds and maintains a table called a MAC table that matches a destination MAC address with a port that is used to connect to a node. For each incoming frame, the destination MAC address in the frame header is compared to the list of addresses in the MAC table. Switches then use MAC addresses as they decide whether to filter, forward, or flood frames. Follow along as we step through the process of forwarding a frame. 1. The switch receives a frame from PCA on port 1. 2. The switch enters the source MAC address and the switch port that received the frame into the MAC table. 3. The switch checks the table for the destination MAC address. Because the destination address is not known, the switch floods the frame to all the ports except the port on which the switch received the frame. 4. The destination device with the matching MAC address replies to the broadcast with a unicast frame addressed to PCA. 5. The switch enters the source MAC address of PCB and the port number of the switch port that received the frame into the MAC table. The destination address of the frame and the address associated with the port are found in the MAC table. 6. The switch can now forward frames between the source and destination devices without flooding because the switch has entries in the MAC table that identify the associated ports. VLANs improve network performance by separating large broadcast domains into smaller segments. A VLAN allows a network administrator to create logical groups of network devices. These devices act as if in the device's own independent network, even if the device share a common infrastructure with other VLANs. A VLAN is also a logical broadcast domain that can span multiple physical LAN segments. Within the switched internetwork, VLANs provide segmentation and organizational flexibility. You can design a VLAN structure that lets you group stations logically by functions, project teams, and applications without regard to the physical location of the users. VLANs allow you to implement access and security policies to particular groups of users. You can assign each switch port to only one VLAN, which adds a layer of security if the port is operating as an access port. Ports in the same VLAN share broadcast, whereas ports in different VLANs do not. Containing broadcast within a VLAN improves the overall performance of the network. A VLAN can exist on a single switch or span multiple switches. A VLAN can include stations in a single building or multiple buildings. VLANs can also connect across wide area networks. The process of forwarding network traffic from one VLAN to another using a router is called inter-VLAN routing. VLANs are associated with unique IP subnets on the network, and therefore VLAN design must take into consideration the implementation of a hierarchical network addressing scheme. This subnet configuration facilitates the routing process in a multi-VLAN environment. When you're using a router to facilitate inter-VLAN routing, the router interfaces can be connected to separate VLANs. Devices on different VLANs send traffic through the router to reach each other. If every port belongs to one VLAN and you have several VLANs that are configured on switches, interconnecting these VLANs would require one physical cable per VLAN. When the number of VLANs increases, so does the number of required interconnecting links. Ports are then used for inter-switch connectivity instead of attaching in devices. To fix this problem, you can use trunks that allow transportation of frames from different VLANs on the same physical link. A trunk is a point-to-point link between one or more Ethernet switch interfaces and another networking device, such as a router or a switch. Ethernet trunks carry the traffic of multiple VLANs over a single link and allow you to extend the VLANs across an entire network. A trunk does not belong to a specific VLAN. A trunk is a vehicle for VLANs between switches and routers. A special protocol is used to carry multiple VLANs over a single link between two devices. Cisco supports the 802.1q trunking protocol for Ethernet interfaces. A trunk could also be used between a network device and a server or other device that is equipped with an appropriate 802.1q capable network interface card. When Ethernet frames are placed on a trunk, the Ethernet frames need additional information about the VLANs that the Ethernet frames belong to. This task is accomplished by using the 802.1q encapsulation header. The 802.1q standard uses an internal tagging mechanism that inserts a 4-byte tag field into the original Ethernet frame between the source address and type or length fields. Because 802.1q alters the frame, The trunking device recomputes the frame check sequence on the modified frame. A 12-bit VLAN ID field within the tag is used to specify the VLAN to which the frame belongs. A tiny part of the 4-byte tag field, 3 bits, is used to specify the priority of the frame. The details are specified in the IEEE 802.1p standard. You can configure an interface as trunking or non-trunking, or you can have the interface negotiate trunking with the neighboring interface. By default, all configured VLANs are carried over a trunk interface. Cisco switches have a factory default configuration in which the various default VLANs are pre-configured to support various media and protocol types. A good security practice is to separate management and user data traffic because you do not want users to be able to establish telnet sessions to the switch. If you want to communicate with the Cisco switch remotely for management purposes, the switch must have an IP address. This IP address must be in the management VLAN, which by default is VLAN 1. An 802.1q trunk and its associated trunk ports have a native VLAN value. When configuring an 802.1q trunk, a matching native VLAN must be defined on each end of the trunk link. 802.1q does not tag frames for the native VLAN. Therefore, ordinary stations can read the native untagged frames but cannot read any other frame because the frames are tagged. A good security practice is to change the native VLAN to something other than VLAN 1, for example VLAN 98, and tag native VLAN traffic. Ensure that the native VLAN for an 802.1q trunk is the same on both ends of the trunk link. If the ends are different, Spanning-Tree loops might result. If IEEE 802.1q trunk configuration is not the same on both ends, Cisco iOS software will report error messages. Also ensure that native VLAN frames are untagged. Dynamic Trunking Protocol is a proprietary protocol that manages trunking negotiation between Cisco switches. DPT allows 2 switches to automatically negotiate a trunk link. By default, all VLANs are allowed on the trunk. Trunk encapsulation must match on both sides. If using IEEE 802.1q trunking, native VLANs must match on both sides. DTP offers 4 switch port modes: switch, trunk, dynamic auto, and dynamic desirable, which can auto-negotiate the operating mode. Cisco VLAN Trunking Protocol is a Cisco proprietary protocol. VTP allows us to automatically add or remove VLANs across multiple switches by performing the operation on just one switch. The VTP protocol operates in a client-server manner and allows one or more of the switches to be used as management point for configuring and distributing VLAN database information in the network. Other switches in the network environment are configured in the role of VTP clients in order to receive VLAN database updates from the switch that has been configured as the VTP server. The group of switches participating in VTP exchanges is considered to be a VTP domain. VTP information is only carried over the trunk links between switches. VTP has 3 modes of operation. Server, this switch generates configuration advertisements and propagates them through the network. Client, this switch only listens to advertisements, updates the VLAN switch database, and passes the advertisements to downstream switches. Transparent, this switch does not change configuration but passes VTP advertisements along to downstream switches. In order to establish a VTP session, all devices within a VTP management domain must be configured to have matching VTP attributes. Devices must run the same version of VTP. There are 3 versions of VTP protocol. VTP version 1 is the default. Devices must be configured with the same VTP domain name, and all devices must share the same VTP password. Cisco Discovery Protocol is a proprietary tool that enables you to access a summary of protocol and address information about Cisco devices that are directly connected. By default, each Cisco device sends periodic messages, which are known as Cisco Discovery Protocol advertisements, to other directly connected Cisco devices. These advertisements contain information such as the types of devices that are connected, the router interfaces to which the devices are connected, the interfaces that are used to make the connections, and the model numbers of the devices. A Cisco device frequently has other Cisco devices as neighbors on the network. Information that is gathered from other devices can assist you in making network design decisions, troubleshooting, and making changes to equipment. Cisco Discovery Protocol can be used as a network discovery tool, helping you to build a logical topology of a network when such documentation is missing or lacking in detail. Because Cisco Discovery Protocol operates at the data link layer, two or more Cisco network devices, such as routers that support different network layer protocols, for example IP and Novell IPX, can learn about each other. The Cisco Discovery Protocol can be used on many different types of local networks, including Ethernet and serial networks. Because Cisco Discovery Protocol is a Layer 2 protocol, Cisco Discovery Protocol can be used to determine the status of a directly connected link when no IP address has been configured or if the IP address is incorrect. Cisco Discovery Protocol neighbors are Cisco devices that are directly connected physically and share the same data link. Here we see that the network administrator is logged into a switch. This switch will receive advertisements from all neighboring devices. You can display the results of this information exchange on a console or remote access session that is connected to a network device configured to run Cisco Discovery Protocol on network interfaces. The Cisco Discovery Protocol provides the following hardware and software information about each neighbor device. Device identifiers, for example, the configured hostname of the switch. Address list, up to one network layer address for each protocol that is supported. Port identifier, the name of the local port and remote port in the form of an ASCII character string. Capabilities list, supported features such as whether this device is a router or a switch. Platform, the hardware platform of the device such as Cisco 2800 series router. Notice that the upper router in the figure is not connected directly to the device the administrator is logged into. To obtain Cisco Discovery Protocol information about this upper router from the console of the administrator, network staff could use the Telnet protocol to connect to a switch that is connected directly to this target device. In this lesson, you will learn the challenges associated with physical redundancy in the LAN and be introduced to protocols that are used to manage those challenges. You will also be introduced to several common LAN topologies. In the networking environment, the need for resiliency has become imperative. Most working environments would be severely impacted by a lack of connectivity. With the need for connectivity, ensuring no part of the network becomes a single point of failure is important. In this illustration, PCA is connected to the network with a single attachment to switch 1. Similarly, switch 1 is connected to switch 2 on a single segment, and switch 2 is connected to switch 3 the same way. Finally, PCB has only a single attachment point to switch 3. Any one of these connections or devices could fail, and therefore PCA would not be able to communicate with PCB. With non-redundant topologies, any component or LAN segment could become a point of failure and impact communications for many users. To provide sufficient connectivity and a resilient architecture, multiple switches may be interconnected in a network topology. Adding switches to LANs can add the benefit of redundancy. Connecting two switches to the same network segments ensures continuous operation if there are problems with one of the segments. Redundancy can ensure the availability of the network at all times. However, redundant network designs must be carefully planned to avoid having a single point of failure without creating network loops. The Spanning-Tree protocol provides loop resolution by managing the physical paths to given network segments. STP allows physical path redundancy while preventing the undesirable effects of active loops in the network. STP is an IEEE committee standard defined as 802.1d. STP behaves as follows. STP uses BPDUs for communication between switches. STP forces certain ports into a standby state so that ports do not listen to, forward, or flood data frames. The overall effect is that there is only one path to each network segment that is active at any time. And if there is a problem with connectivity to any of the segments within the network, STP reestablishes connectivity by automatically activating a previously inactive path if one exists. These are the steps of the Spanning-Tree algorithm. 1. Spanning-Tree elects a root bridge. The root bridge becomes the switch with the lowest bridge ID. There can be only one root bridge per network. Bridge ID is a combination of bridge priority and the MAC address of the switch. Bridge priority is a number between 0 and 65,535, and the default is 32,768. 2. STP elects a root port for each non-root switch based on the lowest root path cost. The root bridge does not have root ports. Each non-root switch has one root port. The root port shows the direction of the best path to the root bridge. 3. STP elects a designated port for each segment based on the lowest root path cost. Each link will have one designated port. 4. The root ports and designated ports transition to the forwarding state, and the other ports stay in the blocking state. STP path cost depends on the speed of the link. There have been several versions of Spanning-Tree protocol developed. Some of these versions are Cisco proprietary. The following is a list of characteristics of various Spanning-Tree protocols. Spanning-Tree protocol, or STP, assumes one 802.1d spanning tree instance for the entire bridged network, regardless of the number of VLANs. Because there is only one instance, the CPU and memory requirements for the version are lower than for the other protocols. However, because there is only one instance, there is only one root bridge and one tree. Traffic for all VLANs flows over the same path, which can lead to suboptimal traffic flows. Because of the limitations of 802.1d, this version is slow to converge. Per VLAN Spanning Tree Plus, or PVST Plus, is a Cisco enhancement of STP that provides a separate 802.1d spanning tree instance for each VLAN that is configured in the network. Creating an instance for each VLAN increases the CPU and memory requirements, but allows for per VLAN root bridges. This design allows the STP tree to be optimized for the traffic of each VLAN. Convergence of this version is similar to the convergence of 802.1d. However, convergence is per VLAN. Rapid STP, or IEEE 802.1w, is an evolution of STP that provides faster STP convergence. This version addresses many convergence issues, but because this version still provides a single instance of STP, the version does not address the suboptimal traffic flow issues. To support that faster convergence, the CPU usage and memory requirements of this version are slightly higher than those of CST, but less than those of RSTP+. Rapid PVST+ is a Cisco enhancement of RSTP that uses PVST+ and provides a separate instance of 802.1w per VLAN. This version addresses both the convergence issues and the suboptimal traffic flow issues. However, this version has the largest CPU and memory requirements. Multiple Spanning Tree Protocol, or MTSP, is an IEEE standard adapted from RSTP. MSTP allows multiple instances of Rapid Spanning Tree Protocol to be defined in an STP domain. A domain is a set of switches running the same instances of MTSP. Each instance will provide a forwarding tree for a set of VLANs assigned to that instance. This version of STP addresses both the convergence issues and suboptimal traffic flow issues. This version is non-proprietary and requires careful planning and implementation. We will take a moment to consider the benefits and drawbacks of the most common Layer 2 network topologies, beginning with the linear switch topology. The benefits of this topology are as follows: provides a high level of flexibility for switch network layout, requires a minimal amount of cabling, and offers a simple, easy to implement configuration. The drawbacks of this topology are as follows: there is no resiliency to the loss of a connection, and the connection to the router is a single point of failure. Next, we will consider the star switch topology. The benefits of this topology are as follows: it provides a modification to the linear topology, and it limits the number of hops between any switch and distribution switch. The drawbacks of this topology are as follows: the link to the central switch remains a single point of failure, and the connection to the router is a single point of failure. The redundant star switch topology gives us a great deal more resiliency in general. The benefits of this topology are as follows: This topology ensures there are always only 2 hops from another Layer 2 switch. There are no natural bottlenecks in the Layer 2 network. Each access switch can lose a single uplink connection and the network will continue to operate, and the Layer 2 network is maintained even if multiple connections are lost. The drawbacks of this topology are as follows. This topology requires the most complex cabling infrastructure, and there is a chance for multiple network loops to occur in this topology. The ring switch topology gives us a certain measure of resiliency if only one connection fails. The benefits of this topology are as follows. It provides a high level of flexibility for the switch network layout, offers an additional cable connection to close the loop, and there is a minimal level of network resiliency that can recover from the loss of a single connection. The drawbacks of this topology are as follows. This topology is more difficult to implement because the topology requires a resiliency protocol, and the top of the ring can become a bottleneck, and the topology is one big loop that could become a problem depending on implementation. Another loop avoidance protocol that can be used in the redundant switching topology is the Cisco Resilient Ethernet Protocol, or REP. Cisco REP is a Cisco proprietary protocol that provides an alternative to STP to control network loops, manage link failures, and improve convergence times. Cisco REP controls a group of ports that are connected in a segment, ensures that the segment does not create any bridging loops, and responds to link failures within the segment. When REP is implemented, network and application convergence typically occurs within 200 milliseconds and can be as fast as 50 milliseconds when the protocol is configured over fiber optic uplinks. One Cisco REP segment is a chain of ports that are connected to each other and configured with a segment ID. Each end of a segment terminates on an edge switch, SW1 and SW5 in the figure shown. The port where the segment terminates are called edge ports and would be E1 and E2 shown in the figure. These figures show a Cisco REP segment consisting of 8 ports spread across 5 switches. When all ports are operational, as in the figure on the left, the ports negotiate to determine one blocked port, the segment, which is the alternate port. When a failure occurs in the segment, as shown in the figure on the right, the blocked port returns to the forwarding state. This allows data to flow through the port to provide recovery from the outage. The following key points were discussed in this module. LANs can vary widely in size from a home office or small business to a large corporate network. The defining characteristics of LANs include their typically higher data transfer rates in smaller geographic area. Ethernet is one of the most commonly used protocol standards in the local area network. The properties of Ethernet depend on the type of physical medium in use, with coaxial, copper, fiber, and wireless media available. Switches are used as network devices to divide a network into segments and reduce the number of devices that compete for bandwidth. VLANs improve network performance by separating large broadcast domains into smaller segments and allow a network administrator to create logical groups of network devices. In the networking environment, the need for resiliency has become imperative so that no part of the network becomes a single point of failure, but redundancy can also cause unwanted loops in the network. The Spanning-Tree protocol allows physical path redundancy while preventing the undesirable effects of active loops in the network, and Cisco REP provides an alternative to STP to control network loops.